This presentation is a condensed version of a paper originally presented at the 2020 DFI conference in Washington, D.C. The title of the paper is Deflection-Based Design for the Capital Crossing Supportive Excavation, written by myself, Harald Ludwig, and Matt Neerman of Schnabel Geostructural Design and Construction. I have been with Schnabel for over 40 years in several different positions, ranging from R&D engineer to construction manager to regional manager and VP of the Mid-Atlantic region. Presently, I am a senior project manager in pre-construction. My involvement with the Capital Crossing project was as the lead design engineer. Schnabel is a leading nationwide design-build contractor that has been providing customized earth retention and specialty foundation solutions for clients throughout the construction industry for over 60 years. The outline of the presentation is shown here. A brief description of the project is followed by a discussion of design concepts to limit building damage. The support of the Holy Rectory Church, HRC, in the bell tower is then described, followed by a description of the monitoring program. Estimated movements are compared with actual movements. Finally, conclusions are given. In 2014, Schnabel was retained by Balfour Beatty Construction as a supportive excavation subcontractor for the Capital Crossing project, located in Northwest Washington, D.C. This slide shows the garage portion of the project in plan view. The site is approximately 950 feet long and 180 feet wide. The two buildings that will be the focus of this presentation are the HRC and the bell tower. The temporary SOE for the Capital Crossing project consisted of a combination of drilled-driven soldier piles, lagging, tiebacks, braces, underpinning, single auger soil mix walls, micropiles, and a tieback slurry wall. Schnabel designed and installed all of the SOE except for the slurry wall. Over 130,000 square feet of SOE was installed, with more than 1,300 tiebacks providing lateral support for excavation depths of up to 72 feet. The existing buildings adjacent to the excavation are shown in this slide. We had a modern office building, 8-story office building, the Casa Italiana, which was a two-story building with half a basement. Then we had the bell tower, that was 85 foot tall, and the HRC, the Holy Rectory Church. These buildings were supported by a combination of conventional hand-dug underpinning pits, bracket piles, and stiff single-auger soil mixed walls. What is deflection-based design? To reliably estimate movements of the SOE and therefore ground movements behind the SOE that result in limited damage to the buildings within the influence zone of the excavation. This slide presents states of strain in distorting structures. Ground movements consist of vertical and horizontal movements. Vertical movement causes angular distortion, while horizontal movement causes lateral strain. The estimated ground movements behind the SOE are converted to angular distortion and horizontal strains in the adjacent structures. The estimated strains are then used to predict potential building damage per the building damage classification shown in the next slide. The two categories that we're interested in for this project are very slight damage and negligible damage. The goal was to limit any damage to very slight or less. One of the adjacent buildings, the HRC, had beautiful stained glass windows on the south side, which were sensitive to any differential type of movement. Per the descriptions given in the slide, the goal would limit damage to fine cracks with crack widths less than 0.04 of an inch. By definition, the fine cracks could be easily treated during normal redecorating. The lateral displacement of the SOE wall that occurs during excavation is mainly controlled by the relative soil wall stiffness. This is a function of the bending stiffness, EI, of the SOE, the distance L between lateral supports, and the modulus of the soil, ES. The volume of the surface settlement trough can be estimated from the volume of lateral wall displacement. In sands, the settlement profile is modeled as a parabola, with the parabola extending a distance of 2h from the SOE wall face, h being the depth of cut. Lateral soil SOE wall movements consist primarily of cantilever movements due to excavation prior to placing the first tieback or brace, lateral bulging movements that develop below the supports as the excavation proceeds to subgrade, and lateral movement due to rotation of a tieback wall as it settles. On this project, lateral bulging movements comprise the greatest component of the total movement measured. Note that the three components of wall movements listed do not include movements due to installation of the SOE and movements due to translation of the wall to develop lateral resistance of the toe. A section through the HRC is shown here, shows the support, supported by 6 tiers of ties. It shows a test boring or soil boring, which is typical of the site, some fill overlaying, some large deposits of alluvial materials. The soil profile consists mainly of alluvial deposits, as mentioned. A 30H trapezoidal earth pressure diagram was used, plus any building surcharges to provide an initial SOE design. This design was enhanced by deflection-based design considerations. Pile sizes were increased and an additional row of tiebacks was added to the upper 17 feet of the SOE to produce a much stiffer wall. The slide also shows the 2 interior columns, rows of columns at the HRC, and this first row was about 12 feet back from the face of the excavation. The slide presents the plan view of the HRC and bell tower. The top of the HRC building is approximately 50 feet above street grade and has 1 basement level. It is supported by exterior reinforced concrete footings and 8 interior column footings divided in 2 rows running in an east-west direction. The interior column footings are located 12 and 40 feet from the exterior south wall. The maximum depth of cut adjacent to the south side of the HRC was 59 feet. Approximately 26 feet of that was below the water table. Single auger soil mixing was used to support this side of the building. It consisted of drilled shafts spaced at 2.5 foot centers with piles in every other shaft. Up to 6 tiers of tiebacks were used to provide lateral support. The 85 foot tall bell tower has an approximate 14 foot by 14 foot footprint. The tower is supported by a 28-inch thick reinforced concrete mat footing. Excavation was done around 3 sides of the tower. The south side of the tower was excavated to a depth of 56 feet, while the east and north sides were excavated to a depth of 27 feet, immediately adjacent to the tower. Along the east side, at a distance of 18 feet from the tower, the excavation was advanced an additional 32 feet. The final design of the SOE comprised continuous conventional hand-dug pits to support the bell tower. 6 tiers of tiebacks were designed to provide lateral support on the south side of the bell tower. In order to try to limit movement, the design called for 3 tiers of tiebacks to be installed in the first 17 feet of excavation to create a very stiff wall. The first tier support was installed 3 to 4 feet below the top of pile to limit cantilever movements. And tiebacks were locked off at 100% of the design load to further limit deflections. Also want to point out the 2 inclinometer locations, SAA1 and SAA2, call them 1 and 2 from now on. 1 was located about 15 feet from the corner of the excavation, and 2 was located about 50 feet from the same corner. This is important when we discuss movements measured at both locations. An extensive real-time monitoring program was implemented to measure movements of the building and the SOE. Prisms were used to measure exterior building wall movements in 3 directions. Prisms are denoted by the red squares, tiny red squares on the walls, and also on the underpinning pits. 2 inclinometers were attached to 2 of the piles, the 2 we talked about just previously, inclinometer number 1 and inclinometer number 2. Here's the corner of the excavation that I alluded to, 15 feet. SA1 was located 15 feet from the corner, and number 2 is located about 50 feet from the corner. Tilt sensors were used to measure movements of the 8 interior columns of the HRC. A comparison of estimated and actual movements near the inclinometers is shown here. The lateral movement at the pile tops, both pile tops, was on the order of 0.1% ahead of the cut, or less in the case of inclinometer number 1, about half that or a third of that was measured at inclinometer number 2. In both cases, very good performance. The settlement of the HRC at the south wall was in the order of ½ an inch at inclinometer number 2 and 0.15 of an inch at inclinometer number 1. The first interior row of columns, 12 feet from the face of the excavation, exhibited slightly smaller movements than were measured on the wall of the HRC. The slide presents movements of the wall perpendicular to the wall, measured by inclinometer number 2. It's clear that as we installed the first 3 tiers of tiebacks and tested them, that the wall was actually pulled back away from the excavation. And this again was done in order to create a much stiffer wall in the upper 17 feet. As the excavation proceeded, bulging movement started to increase below each tieback elevation. By the time we reached subgrade, we were seeing movements of up to 8/10 of an inch, bulging movements of up to 8/10 of an inch. The movements measured by inclinometer number 1, perpendicular to the wall or into the excavation, are shown here. It's clear that there was more fixity of the pile toe compared to inclinometer number 2, and that there was less lateral movement, but there was still bulging movement up to 4/10 of an inch. And we believe that this was due to the influence of corner effects on the magnitude of movement. Again, inclinometer 1 was located only 15 feet from the corner of the excavation. Other movements were also measured by the inclinometers and the prisms. This graph or figure presents movements parallel to the wall, movements in a west to east direction, which was surprising to us. But these movements were independently confirmed by the prisms located on the HRC structure itself. All of them showed movements from west to east. They showed a block movement from west to east. We observed similar movement patterns for the Casa Italiana and the modern office building. You can see that the magnitude of movement was between 7/10 and 8/10 of an inch in any west to east direction. So what are the conclusions to the presentation? 1, the performance of the SOE met the design goal of limiting building damage to very slight or negligible. 2, the deflection-based design method developed by Cording et al. Estimated both lateral and vertical building movements that were reasonably close to actual building movement. 3, the inclinometer located near the west end of the HRC measured movements that were less than estimated. This was most likely due to the influence of corner effects on SOE movements. 4, for any excavation adjacent to an existing building, the SOE design intent is to limit potential damage to the building. Selecting the earth pressure and surcharge pressure diagrams is just one step in designing the SOE. It is essential to consider the stiffness of the SOE in the design as well. Acceptable potential damage should be agreed upon prior to start of construction. 5, unexpected eastward movement of the buildings as blocks was measured. The reason for this behavior needs to be investigated further. And finally, more case studies need to be done on well-monitored buildings adjacent to excavations to expand the database and on estimated performance versus actual performance. This brings me to the end of the presentation. Thank you very much.